Hi, this is Keith Schneider. I'm a professor in the Department of Food Science and Human Nutrition at the University of Florida. I'm going to give a talk on post-harvest water quality and disinfection, disinfectant use. One of the reasons we spend so much time with post-harvest water is just its ability to make a very small problem into a larger problem. Communal water bath like the flume that you see pictured, or ice used to top produce coming in from the field to remove field heat, all have the ability to spread contamination that might be isolated to a small amount of produce and spread it around to a larger amount, thus increase the potential for having a foodborne outbreak. Water is often a common source for contamination in packing sheds and in the field and packing sheds. Um, Ice is frequently overlooked. Again, it's typically made and then stored on the concrete, right on the ground, and then scooped up with a front loader. So we have to look at that as a potential source of contamination. And any water reuse, flumes and brush beds, anytime we recirculate water, we have to be very careful that we handle that water properly, and again, don't use those as sources of cross-contamination. So let's look at some numbers here. If we look at some of the multi-state outbreaks, and this was some of the more recent information that was gathered in 2019, and this goes from 2010 to 2017. You see the largest number of multi-state outbreaks is associated with sprouts, and then followed by some of the usual suspects: melons, lettuce, um, papaya and cucumber, and then leafy greens and tomatoes. So if we look at this chart, the distribution is again fairly consistent with what we've seen. But if let's take sprouts out for a moment, and we just look at row crops, greens, when we consolidate all those, become one of the largest offenders with about 37% of all the multi-state outbreaks associated with greens. And we just have to go back to the 2018, 2019 romaine lettuce outbreaks to kind of get a sense of that. Then melon and papaya, cucumbers, and tomato. So again, these are some of the usual suspects. And one of the things we want to do, especially with post-harvest water, is to limit the potential for a foodborne outbreak. Now, it's almost impossible to prevent a foodborne outbreak in the field. While we do have the produce safety rule and programs like the Leafy Greens Marketing Agreement and the TGAP program in Florida, getting or preventing 100% is almost impossible. So the goal of post-harvest water is to limit those or limit the potential of those as much as possible. So these are straight out of the PSA training guide. So just wanted to point out some of the rules, what's in the rule. For post-harvest water, you can have no detectable generic E. coli in 100 mils. The Food Safety Modernization Act, Produce Safety, does not require water to be treated. Though any antimicrobial products are considered good practice, and they're also considered to be very valuable in that they can prevent the buildup of microorganisms, aka biofilms, on food contact surfaces. The one thing I want to point out on this slide, though, is that on single pass water, it's not required to have any type of sanitizer at all. So even though it's recommended, it is not required by law to actually use a sanitizer. Now, that's not the case for the TGAPS program, where you do have to use a required amount of sanitizer in the water, if in fact you do use any type of wash process. Same goes for recirculated or batch water. Again, the water quality, straight out of the producer safety rule, is no generic E. coli per 100 mils of sample. But you have to maintain that water quality throughout its use. So if I'm recirculating a flume tank for 6, 8 hours, even though at the beginning at that processing day I have zero E. coli, even though and I'm recirculating it, I have to maintain zero E. coli. Interestingly enough, a treatment is not required to maintain water quality or to prevent cross-contamination. And the question is, well, how do you do that? And the answer really is you don't. But again, if you are going to use an antimicrobial to meet this water quality standard, you must be labeled for the appropriate use. So it has to have that EPA registration number, and it has to be labeled for the washing of fruits and vegetables or the treatment of flume water, but it has to be for specific use. If you use batch water or recirculating water, you have to have some way of changing it or some frequency of changing it. And again, the use of these sanitizer antimicrobial products are really recommended for the prevention or buildup of biofilms on these surfaces, which again can exacerbate the microbial load and potential foodborne outbreaks. So things to consider. Sometimes you hear you want to start with water equivalent to drinking water. That's not necessarily true. The water used for post-harvest does not have to be potable. It just has to meet the zero E. coli standard. So sometimes you will hear drinking water quality. That's not the case. All we're looking for is no generic E. coli per 100 mils. But that does then exclude the use of untreated surface water. But we still don't have to meet the municipality regs, which are much stricter than what the PSA outlines. If you're going to use a sanitizer, we have to make sure you're using a food grade sanitizer. Again, we mentioned EPA registered for intended use. And while it's not required, it is recommended. If we're going to use water in a flume, hydro cooler, or some type of chiller, we have to have some frequency that we're going to exchange that water when we think it's no longer fit for use. There is also the requirement or recommendation that the temperature is acceptable to reduce any type of infiltration due to the temperature differential between the recirculating water and the fruit itself. And then lastly, the sanitization of any food contact surface. And again, post-harvest water goes from tools, scissors, or shears used in the field all the way to the equipment that's used for packing. And there's just a couple of links for you to look at. To get my water to the level I would like, I could use some type of antimicrobial device. I could use UV light, an ozone generator, some type of filtration system. I can use EPA registered antimicrobial pesticides or sanitizer solutions. They can be chlorine based, things like sodium or calcium hypochlorites. I can use proxyacetic acid, hydrogen peroxide, again, ozone. So there are any number of choices out there that you can use. You just have to pick one that is safe to use and is allowed to be used on the crops that you're harvesting. So what I want to do now is I'm going to specifically talk about chlorine-based sanitizers because they're the most frequently used. And what we typically are looking for is a residual in the water. And there's a couple of different things we want to consider. One is how we're going to measure that, and we can use things like test strips, as you see in the picture there. I can use a handheld spectrophotometer, that picture on the upper right. But again, we just want to make doubly sure that it is a food grade chemical and that you're using it at the appropriate levels. And that's according to the manufacturer's recommendations and what it is registered at. And anytime we use any type of antimicrobial in the water, we want to make sure that we have some type of monitoring in place. Again, if we're going to use a particular chemical, we want to make sure that it's applied to the standard that we've adopted and that it's being applied at the rate that we know is efficacious. One thing to consider anytime you're using any type of sanitizer in a recirculating system is that there's going to be organic load, and that organic load is going to compete um, for the chlorine or the free chlorine or the oxidant in the water. So this is a concept known as breakpoint chlorination, and it's this is typically something you think about again in wastewater treatment, but it applies to any type of chlorination like you would use in a flume tank. As you begin to add chlorine to any system, the first thing it's going to do, that chlorine is going to start to bind up and oxidize materials in the water. And you're going to start producing combined chlorine compounds. And if there's nitrogen in the water, chloramines, mono, di, trichloramines. And at a certain point, once all of the available material has been oxidized or bound up, then and only then do we get free chlorine being released. And that's known as the break point. You can kind of see that on that graph there. And as you add chlorine after that, we see a rise in the amount of free chlorine that we're able to read within the tank that we're using. So whenever we're adding, we have to kind of consider that there's going to be a certain amount of chemistry that we use that's not going to be being used for disinfection at all, but rather just going to go to oxidizing those organic compounds that are in the water. And as the quality of the water changes throughout the day, we have to take into account that we're going to have to add more chemistry per hour to overcome the organic load as that water gets dirtier and dirtier. At a certain point, it's going to be to a point where the chemistry is not going to be efficacious at all. And this is why when we get to a system, we want to make sure that we change the water on some regular basis. So if we look at total chlorine, we put in a certain amount, let's just say 100 ppm, but that 100 ppm, especially if we're putting it into a water that's not quite clean, we're going to get a certain amount of free chlorine, and then we're going to get the combined chlorine. So who knows, maybe out of that 100 that I put in, I may get 60 free chlorine. So you're thinking, okay, I'm putting in 100, I'm going to get 60, and that's what I'm going to work with. But there's also another problem that you have to consider. Hypochlorites, things like sodium and calcium hypochlorite, will produce hypochlorous acid, that HOCl compound, and that's considered free chlorine. But there's also a portion of that that is in the ionic form, the OCl minus hypochlorite ion, which is also considered free. The difference is that HOCl is much more efficacious than OCl minus. So out of that 60, depending on my pH, I may only have half of that 60. So now out of the original 100, I may only have 30 ppm of HOCl, which is my free and active form of chlorine actually doing any type of disinfection. So here's what that looks like. Anytime I put any type of hypochlorite in the water, I'm going to produce hypochlorous acid. That's the species I want. And whether it's sodium, which is in a liquid form, calcium hypochlorite, which is in tablet form, or even chlorine gas. When I put any of those into water, what I'm going to end up with is HOCl. That HOCl is going to differentiate or dissociate into OCl minus. And this really depends on the pH, and that the curve that kind of shows that is here, where around pH 7.5, 7.6, I'm going to get the 50-50 point, where if my pH is at 7.5, 50% is going to be in that HOCl form and 50% is going to be in the OCl minus form. So whenever you're trying to figure out effective dose, you have to first figure out, again, how much I need to achieve breakpoint, and then whatever my free chlorine reads, I can tell how much of the active form is by just knowing the pH and using a chart like this. So if I want to be more efficacious, I can lower the pH. If I lower the pH to say 6.5, I'm going to have roughly 90% in the active form. which again increases the efficacy, but I have to add an acidulant. If I let the pH go up, say to 8.5, the reverse happens. I only have about 10% in the active form and 90% in the inactive or less active form of hypochlorous acid. Now, what if you say, I don't want to mess around with pH at all? Well, here's an example where more is not better. So let's start out where we have 200 ppm. That's our total chlorine that we're going to put in the system. We take a reading and we're at pH 6.5. Let's just say this is all in the free form. And then I'm going to use in another tank 2000 ppm. But since I'm not adding any acid to this system, I'm just going to let the pH naturally settle. And again, at 2000 ppm, the pH would probably be slightly higher than 8.5. It might be 9.5. But for the sake of this argument, let's just say it goes up to 8.5. So in example one, I will have 90% of that 200 ppm in the active form, or roughly about 180 ppm in the HOCl minus form. In the second example, I'm going to end up with about 10% in the active and free form, which is roughly 200 ppm. So I've added 10 times the chemistry for about the same efficacy. Almost the same amount of active, free, and active chlorine are left over. So if you visualize this, by just adding an acidulant to that initial 200 ppm solution, I can increase the efficacy up to 90%, and I save a lot of chemistry. Now, what we don't want to do is continue to add acidulant. Well, 6.5 is great. Why don't we go to 5.5 and make it 99%? Well, as we get closer to 5, that curve starts to drop off and the amount of HOCl begins to drop again. We start producing chlorine gas. And at that point, we end up with a very dangerous situation. It's one of the reasons when we talk about household disinfections, we tell people never to mix vinegar and bleach because you can get the elution of chlorine gas, which can be a major health hazard. So our target zone typically is between 6 and 7.5, but most applications 6.5 to 7.5 usually gives us anywhere from that 80 to 50% in the free and active form is what we're looking for. Now, one thing we have to be very cognizant of is the amount of organic material in the water, and that will quickly build up over time. And the more organic material we have in the water, the less of the sanitizer we're going to have to react and kill the microbes. So we want to keep an eye on how much we have in there. And one method people commonly use is ORP meters, oxidative reduction potential meters. And as the ORP drops, this can be programmed into a pump to turn on and apply more chemistry and to bring the ORP back up again. And that's a good way of distributing chemistry. ORP doesn't give a great estimation of what amount is there, especially as the organic matter builds up. That ORP measurement becomes less reliable, but it's still a good way of introducing sanitizers into a system. But you got to be very cognizant, and then we have to develop some type of frequency. And again, we could use things like a handheld turbidity meter or even just a simple comparison chart to determine the frequency which we want to change our wash water with. As with any process, again, we want to monitor the sanitizer use, make sure that we take routine measurements. Even if we have an automated system that's using something like ORP, we still want to take maybe hourly measurements of that system to make sure we're getting an accurate reading of the sanitizer, especially in a recirculating system, and that we're getting the efficacy that we're looking for. Anytime we're changing the water, water quality testing, especially again if we're using municipal water or even well water, to fill these tanks again to make sure that we meet that minimum quality of no E. coli per 100 mil. So in summary, one, post-harvest water should start out clean. Again, we're looking for the level to be 0 E. coli per 100 mil, or no detectable E. coli per 100 mil. Uh, in a single pass or even recirculating system, we have to maintain that water quality. And remember, it is not required by FDA that you use a sanitizer, but it's highly recommended. And again, it's almost impossible within a recirculating system to not use some type of either device or sanitizing agent to maintain that water quality. Don't forget about ice. It's one of those things that I've often forgotten about. Those systems need to be clean. We have to make sure that, again, if we're topping um, produce coming out of the field, that again, we're making sure that ice is clean. Preferably, we're not contaminating it by producing and then storing it on the ground. It's a very difficult situation to kind of manage. And lastly, just make sure they're using EPA registered chemistries and using them correctly. So that's my time. Again, I'll be able to answer questions if we have that capability. And thank you very much for your attention.